Hi, this video is going to wrap up our coverage of the vector-based queue. Here we're going to get the final draft of the data structure and we'll look at code for that. So let's recap where we left off in our second draft. As of the second draft of our vector-based queue, we had a partially filled vector and it had this wraparound feature. So the idea is that we store the elements of the queue in a vector. The data members of our vector-based queue are that vector object, the index of the front element. So in this sketch, I've got a queue containing 7, 1, and 4. 7 is the front element of the queue, and front is at index number 2. So the used part of the vector starts at index number 2 with the front of the element, front of the queue, and then we also have a size data member to keep track of the size of the queue. In this sketch, it would be 3. It's a partially filled vector, so some elements of the vector are in use, storing queue elements. Other elements are not currently in use. They can be recycled. The unused elements are drawn as question marks in the sketch. And the indices wrap around. That was the big problem that we solved in our second draft in the previous video. In our first draft, we had this issue where if you kept enqueuing, eventually you would try to go off the end of the vector and have an out of bounds exception or crash. And that's not really okay. To solve that problem, what we did was we have the indices wrap around. So if we go off the end of the vector, instead of just giving up or crashing or something, we start recycling the indices at the beginning of the vector, number 0 at the beginning there. So in this sketch here, if I enqueued another element, it would go at index 5, which is no big deal. If I enqueue another element, then we would store that new element at index 0 at the beginning, and we call that a wraparound when it's going back and using the first index again. That means that we can enqueue, dequeue indefinitely. So the second draft of our vector-based queue can handle enqueue, dequeue, alternating like that, very long and not wear out or crash or anything like that. But there's still one problem with this draft of the vector-based queue, which is that it has a fixed capacity. If I have a 6-element vector, then I can never store more than 6 elements in my queue. And that's a pretty big limitation. We want to make it so that we can store any number of elements in our queue. So what we're going to do is reuse an idea we covered earlier, which is the resizing idea. So remember back when we were implementing vector, we had a similar kind of a problem. The vector stored its elements in a fixed length array. It was a partially filled array, but that partially filled array could overflow. The overflow would happen if you tried to add an element to the vector that can't fit in the array. And the solution to that problem was to resize the array when needed. So if we're in a situation where we're trying to add one more element to the vector and doing so would overflow the array, we just make a new bigger array. We in fact doubled the capacity of the array, so we allocate a new array that's twice as big, copy the elements out of the old small array into the new big array. That whole process takes linear time because of the copying loop. However, it happens less and less frequently as the vector gets bigger and bigger. If we keep doubling the size of the vector, eventually it gets pretty big, and you don't need to resize it very frequently, if at all. And so the mathematical analysis was that this resizing behavior doesn't really change the runtime of the vector very much. Adding an element to a vector still takes constant amortized time. We're going to apply that same idea to our queue. So we're going to have resizing in our queue. If the queue would overflow, meaning the queue is currently full with its size and capacity the same, and we're trying to enqueue one more element, we'll resize. So when we resize the queue, we'll double the size of the element vector, copy everything out of the old small vector into the new big vector. There's one detail here, which is that the front of the old vector might not be at index number 0, it could be anywhere. To make that copying simple, what we'll do is we're going to start over and have the front of the new big vector be index number 0. So we always copy into the new big vector starting at the beginning at index number 0. The same kind of mathematical analysis of vector resizing applies to this situation. One queue resize takes linear time, but enqueuing an element to the queue will still only take constant amortized time because the resizing gets very rare. Now let's finally look at some code. So here's my class vector queue. The data members are down here. I've got my size t size and first, and then we have the vector of t's called vector that actually stores the elements. That's all I need for data members. It's a container adapter, so it's pretty simple in that way. The constructor just needs to initialize size to 0 and front to 0 and doesn't do anything else. by default, the vector constructor initializes itself to a valid empty vector. That takes constant time. And the size accessor just returns the size data member. That's a very simple one-line implementation that takes constant time. Now let's look at the front operation. This gets the front of the queue. And first we check that if the queue is currently empty, then we throw an exception because there is no front element. If we get past that check, then we return the element at the front index. So return vector at index front, that's all there is to it, and that takes constant time. Okay, enqueue is similar to our previous draft. There's just the extra resizing logic. So before we try to access an element that may not exist, we say if size plus 1 is greater than the vector size, that means there's no room for another element. You know, if I were to add one more element to our queue, it would be bigger than the capacity of the vector. So if we're currently full and there's no room, I do a resize. This if statement guarantees that we have at least one available element in the vector. From then on, it's exactly identical to the second draft of our code. We compute the index of where the back of the queue should be, which would be the first index plus the size, mod vector.size to do the wraparound feature. Then vector at index I is equal to x, and we increment size to keep size accurate. So all of this takes constant amortized time. All of the code depicted here explicitly takes constant time. The if statement, I, the assignment, and the plus plus size. And then resize takes constant amortized time because of the same kind of analysis as we had for vector resizing. Let's take a look at that resize function right now. It's pretty similar to the vector resize private function. Note that this is a private function. It's only called by vector itself. The client can never call resize themselves. We calculate what the new size should be. That would be basically size times 2, but we say the maximum of size times 2 and 1. This is so that if the current size is 0, when we do size times 2, we won't try to resize to 0 again and have some kind of like infinite loop where it never gets bigger. So ordinarily the new size is twice the current size, but if the current size is 0, then the new size is 1, is what this does. I make a new vector of that size, twice as big, and then here's the loop that copies everything out of the old small vector into the new big vector. I goes from 0 to the current size, I++, and what I need to do is calculate the index of the ith element in the old vector. So that would be front plus I. And then remember, anytime we're increasing an index, we do mod vector size to do the wraparound behavior. So the index that we're going to pull from, I call it j just to make this clear. J is front plus I mod vector.size. So that's taking the ith element out of the old smaller vector. New vector at index I starting from 0 is equal to vector of j. So after this for loop finishes, we copied all the elements out of the small old vector into the new big vector. Then the two vectors swap, so they exchange their contents, and now vector holds the new larger vector object, and the new size variable is holding the old small vector, and new vector goes out of scope right here and gets freed automatically due to RAII. Finally, the one detail of front, we set front to 0 because that's where the front of the vector is now. Note that we don't change the size because the size is still the same. We didn't change the number of elements in the queue, we just changed the capacity of the vector that holds them. So this is linear time when it happens. Okay, finally let's look at Dequeue. That removes the front element from the queue. We check if size is 0, we throw an exception. You can't do that. Then we compute where the new front should be. So that would be the current first index plus 1 mod vector.size. That's the new front index. We decrement the size to keep that accurate, and then we just have a little check here. If the vector is now too small where very few elements are being used, we do resize as well. So if vector size is greater than or equal to 3 times size, that means if we're using less than 1/3 of the elements, then we shrink the vector. So this takes constant amortized time as well. Okay, so here's a summary of the vector-based queue. The default constructor, size, and front operations take constant worst case time, just constant time no matter what. The operations that change the size of the queue are constant amortized time. NQ of x takes constant amortized time, and DQ takes constant amortized time. And the reason the amortized word is there is because occasionally those operations resize the vector, so we have to say amortized to be honest about that.